Okay, this lecture in this lecture we are going to discuss about the mechanical vibration. Okay, vibration occurs in mechanical systems. Okay, the vibration we can call it as simply we can define the vibration oscillatory motion of an object, the back and forward motion and object. We can call it as a vibration. Okay, in a mechanical system to generate the vibration there should be a stiffness and the mass. Okay, that mean this oscillatory motion generate in a mechanical system because of energy transfer from potential energy to kinetic energy. So that to store the potential energy there should be a stiffness, to store kinetic energy there should be a mass. Okay, then this is the vibration common in mechanical systems. Okay, the most of the cases the vibration have to control or minimize. Okay, so then in this lecture we are going to discuss what are the governing parameters of the vibration system in a vibration, and also how to control this vibration, what are the mode of vibrations. In these things we are going to discuss in detail. Okay, first we are going to start with the free vibration. So vibration without damping, then we can go for next further topics. Okay, let's move to the today's topic about the free vibration without damping. Okay, today's topic is about the mechanical vibration. Okay, today's topic is about the mechanical vibration. So mechanical vibration means the vibration occurs in the mechanical system called the mechanical vibration. Okay, first let me define the vibration. What is the vibration? Okay, here we are discussing the mechanical vibration. Okay, there's a electrical vibration, the magnetic flux vibration, but this lecture is focused into the mechanical vibration. The vibration occurs in the mechanical system. So what is the vibration? The oscillatory movement of an object. Let's take certain object. If it is produce oscillatory movement, back and forward motion, okay, back and forward motion, repetitive motion, called vibration. It may be a periodic, it may be a unperiodic. Okay, the oscillatory motion and object is called vibration. Okay, then in this lecture we are focusing to the mechanical vibration. The vibration occurs in mechanical system. Okay, to produce a mechanical system, mechanical vibration, there should be a stiffness and the mass. In a mechanical vibration generate due to the energy transfer in between potential energy to the kinetic energy. Potential energy to the kinetic energy. Okay, this mechanical vibration occurs due to the energy transfer in between the potential energy to kinetic energy. Okay, then to store the potential energy there should be a stiffness. Okay, the way of that means stiffness, or there should be a gravitational, that means the height difference. Okay, then there should be a method to store the kinetic energy. There should be a mass to store the kinetic energy. Okay, then this potential energy in most of the cases is stored in a stiffness. We can simply say half into k x square o mgh. There's a two generally in two methods, the stiffness of a stiffness and also the gravitational potential energy as the two types. Okay, then the kinetic energy half into k half into mv square, half into mv square. Okay, the kinetic energy and the potential energy. So the energy transfer in between these two potential energy to kinetic energy, the mechanical vibration occurs. Okay, so if system to produce the mechanical vibration, there should be a mass, and also there should be a method to store the potential energy. It may be a stiffness, maybe a height difference, reference to the certain gravitational level. Okay, then for in this mechanical vibration, we can draw the equivalent system. For example, let's take for example, let's take this is the table. These are the legs of the table. Then if we give some certain energy, the table vibrate. So then we can draw the this is mounted on the legs of the table. Then we can, for this system, we can draw the equivalent system. This is the equivalent system for this vibration analysis. The table top we can give the mass, and also the stiffness of the legs we can represent by a stiffness spring. This is the equivalent system. Okay, always we are drawing this equivalent system for a given system to analyze the vibration. Okay, then we are finding the equivalent stiffness, we are finding the equivalent mass value, then we can mathematically analyze this kind of system. Okay, then okay, then every mechanical vibration system, there is a mass and the stiffness. I will draw every mechanical system, there's a mass and this stiffness, and also there are also available damping. Okay, every system containing, in a real world, every system containing these things in a mechanical vibration, there should be a mass, the K, this K is represented the stiffness. That means there should be a method to store the potential energy. It may be a gravitational potential energy or stiffness of a certain object. Then there are also a associate damping. Damping means the energy dissipation method. Okay, energy dissipation method. System energy dissipate because of the damping. Okay, there's a then let me define this damping. The dissipation method, energy dissipation method is called damping. Okay, energy dissipation method is called damping. Okay, is called damping. Every mechanical vibrating system associated with the damping. That means the energy dissipate so that the vibration amplitude diminish or diminish. Okay, so then let's find this what are the method for this damping. Okay, damping methods. Okay, there's a three method of damping in a mechanical vibrating system. So what are these three methods? First one, viscous damping. Viscous damping, dry friction damping, third one, hysteretic damping. viscous damping, dry friction damping, hysteretic damping. These are the three methods to dissipate vibration energy from a vibrating system. Okay, first let me elaborate this damping method. Let me take the first one, the viscous damping. Okay. Okay. Viscous damping. The viscous damping means damping due to the viscous friction. Damping due to the viscous friction is called viscous damping. Damping due to the viscous friction is called viscous damping. Then you all know when the object moving on a viscous fluid, let's take the viscosity is eta. If certain object moving on a viscous fluid, let's take the velocity v. In opposite direction there is a force is generated. Because of the viscous friction. This is called viscous friction force. This force is proportional to the moving velocity. Okay, this viscous force is proportional to the moving velocity. That is given, that equation is called the Newton's viscous friction force equation. Then we can write this one as F is equal K into V. F is equal K into V. The K is a constant. K is a constant that is depend on the K depend on the viscosity of the fluid and also the properties of the surface property of the object. Okay, then you can see if this method we can use to apply the damping for the system. For example, let's take this kind of system. Previously I took the spring mass system. Again let's take, this is the spring, then I am taking this kind of viscous fluid container, then this is the object. Okay, let's consider this system. What can you say about this system? There is contain the stiffness, the mass and the viscous fluid. Okay, then what happened? Let's take, this is the equilibrium position. When it moves in certain direction, let's take the system is vibrating middle of this equilibrium position, around this equilibrium position. When it moves in one side with a certain velocity, extort velocity, let's take the first certain situation having the extort velocity, the opposite friction force is acting. Due to the viscosity of the fluid. So what is that friction force? F is equal K into extort. You can see when this M mass is moving in downward direction, the energy is consumed to do work against this force. Okay, energy is consumed to do work against this viscous friction force. Okay, when it move downward, what happen when it move in upward direction? Same thing, no? Same thing. It having the certain velocity. When it move in upward direction also, certain energy has to waste to do work against this friction force, viscous friction force. That means in each cycle, in each cycle, the energy, certain energies dissipate. Energies dissipate from the system. Okay, certain energies dissipate from the system. This energy dissipation method is called viscous damping method. Okay, this is the basic principle used to design the vehicle shock absorbers. Okay, this is the basic principle used to design the vehicle shock absorbers. Vehicle shock absorbers also having this kind of viscous fluid, and instead of this, it is moving object. It is transferred to the another chamber through the small orifice. Okay, same thing happen when it transfer from small orifice. Certain energy is consumed to do this work. Okay, then in detail we are going to discuss this viscous damping later. We are obtaining the equations. We are going to mathematically model this kind of system in later. Okay, then viscous damping. Then next damping method is dry friction damping. Next damping method is dry friction damping. Second one, dry friction damping. Dry friction damping, let me take the example. Let's take this kind of stiffness. Then it is on the rough surface. This is the mass, this is the stiffness. Then it is placed on a rough surface. Okay, we are given certain energy to the system to start the vibration. Then by taking this E energy, start the vibration. Let's take it is moving in this direction. This by taking this this is the center as the vibration. What happen when in each movement, let's take if it is moving in this direction, in opposite direction the friction force is acting. But in this situation, this friction force is a constant. That is not depend on the velocity. That is not depend on the velocity, but it is friction constant. Friction force is a constant. Then what happen? This given energy consumed in each movement because of this friction force. That means to do work against this friction force, the system energy consumed. So then what happen? The total energy of the system reduces gradually because of this energy dissipation. This method is called dry friction damping method. This one also used in mechanical system to minimize to control the vibration. Okay, to control the vibration. Then next one, the third example, the hysteretic damping. Hysteretic damping. Okay, so let's take for example, let's take hysteretic damping mean, for example, let's take spring mass damper system, the system we previously took. Let's take this is the mass, this is the stiffness. Let's take this this is placed inside a perfect vacuum. There's no air friction, there's no any other contact in body, or there's no air friction even. So then we are given, let's take we are given certain energy to the system through the magnetic. Let's take this is the there's a ferrous metal part, then from the magnetic pulse, we are giving certain energy to the system. Okay, so what can you say about this vibration of the system? It is vibrate forever. Is it vibrate forever? No. Is it not vibrate forever? So why is that? How the energy is dissipate from the system? System amplitude gradually diminish. It also vibrate, forming a diminishing amplitude like this. So why is that? So energy dissipate from the spring. In each vibration, actually this energy is dissipate as the form of heat, mostly as the form of heat. Okay, mostly as the form of heat. Then how the energy dissipate from this heat? What happen in each deformation of the spring? That means the deformation of this material of the spring, the breaks the existing bond and the forms the new bonds. Okay, in each deformation this happen, the existing bond break and new bonds are formed. In each break in the bonds and the form in the new bonds, they consume certain energy. That energy taken from this system energy, vibration energy. So that the energy is dissipate due to this deformation of the material, because of this changing of this internal molecular structure, then this energy is dissipated as the heat. Okay, heat. Then you can observe this one as the in practically the after certain running period, if you can observe the coil spring of a vehicle. If you touch the coil spring of a vehicle after certain journey, that will you can observe that has heated because of the hysteretic energy dissipation method. These are the three methods for energy dissipation. What are these three methods? The viscous damping, the friction damping, and the hysteretic damping method. Okay, then the vibration energy reduce. The vibration energy, every real world system associate with one or more these damping methods. Okay, one or more, mostly the three, most of these in the most of the cases, every system associate with these three damping methods. Okay, not only one. Then because of this reason, the amplitude reduce, then gradually the amplitude of the vibration diminish. Okay, then next we are going to discuss in detail about the free vibration without damping. Okay, this is ideal situation. First we are going to discuss about the ideal situations. Okay, the first we are going to discuss about the free vibration without damping. Okay, free vibration without damping mean actually it's ideal system. In the real world we can't find this kind of system. The damping is equal to 0. That means that there's no energy dissipation. Okay, there's no energy dissipation. Actually it is a ideal system. So the equivalent model for this kind of system we are drawing in this way. This is the equivalent system. The mass and the stiffness. This is the ideal system we are drawing this for the free vibration analysis. Here the mass to store the kinetic energy, the K, the spring is representing the energy stored in the energy and potential energy storage. Okay. Then let me obtain the equation, the chaostatic equation for this motion of this object system. It's a mechanical system. The mechanical system means its behavior and operation we can represent, explain by using the mechanical theories and principles. That's why it's called the mechanical system. This is a mechanical system. Okay, the vibration theories we can use to explain the behavior of this system. That's why it's called mechanical system. Okay, let me obtain the chaostatic equation for this system. Chaostatic equation for this system. Okay, let's take original length of the spring as before placing this M mass. Let's take its y, original length of the spring. So then after placing this M mass on this top of this spring, the spring is compressed. Let's take the length is y dash. Okay, then we are given the certain energy. Certain energy to the system. Okay, certain energy to the system. Then system will start the vibration. Then let's take the certain moment. Let's take the certain moment. It is in vibrating. Certain moment mean let's take this the equilibrium position. Let's do the equilibrium position. Then from the equilibrium position, let's take the movement as x. It the situation that T is equal T. Let's take it as produce the x displacement from the equilibrium position. This is the equilibrium position. Then spring has further compressed. Okay, let's take the spring length as now y double dash. Okay, y double dash. Okay, before going to obtain this chaostatic equation, first let me define this what is known as the free vibration. So what is known as the free vibration? Vibration without any further disturbance. Vibration of a system without any further disturbance to the system is called free vibration. Any further disturbance means there is an initial disturbance. Okay, there is an initial disturbance to the system, then there is no any further disturbance to the system. Okay, that means for this system, initially to start the vibration, we have to give the certain energy transferring activity. Disturbance means for this situation, for this when talking about this mechanical vibration, disturbance to the system means any energy transferring activity. In any energy transferring activity is called disturbance to the system. Energy taken out from the system or given to the system called disturbance to the system. After initial disturbance, to start the vibration, we have to give the initial disturbance, energy transfer. We have to give the energy to the system. Then there is no further disturbance to the system. There is no further energy transferring activity. Called free vibration. Okay, called free vibration. That's why I call the free vibration. Then without damping, there is no damping method. Diffusion, viscous damping, or any hysteretic damping, there is no damping method. Theoretically, system vibrate forever. System vibrate forever theoretically. This is a theoretical system. First, we are going to start this theoretical system. Okay, that is not real. Then let me obtain the equation for this one. Let me just move to this diagram. The equation of the motion. Equation of the motion. Then okay, let's take equation of the motion. Let's take we are going to let's take this is the x displacement. It has produced the x displacement in vibration. Let's take the the velocity x dot, and also the acceleration x double dot. Okay, acceleration also double x double dot. So let me obtain the equation for this one. So I am going to put the F is equal ma, the Newton's second law considering the motion of. I am going to put F is equal ma considering the motion of m mass. Okay, I'm going to put the F is equal ma, consider the motion of m mass. Okay, then what are the forces acting on in downward direction? mg. Okay, in a downward direction mg. So then what are the opposite direction? The stiff spring force is acting minus k. What is the total compression of the spring? Here y minus y dash plus, from this it also displays x distance, x is equal mx double dot. Okay, so then we can further simplify this one. mg minus k y minus y dash into minus kx is equal mx double dot. Okay, so then you can see the mg is equal k y minus y dash. In a static situation, this is the deflection. In a static situation, this is the spring length is the y dash. The total compression in a static situation, y minus y dash, k into y minus y dash should equal to mg. So then we can cut this one. So finally we are having the equation m is equal mx double dot plus kx. Further we can simplify this equation. 0 is equal x double dot plus k divided by m into x. Okay, then 0 is equal d2 x dt square plus k divided by m into xt. Okay, this is called characteristic equation of the system. Characteristic equation of the system. You can see it's a second order. Homogeneous ordinary differential equation. Second order homogeneous ordinary differential equation. Then what is the solution of this kind of differential equation? I think you all familiar with this differential equation. You may familiar with this differential equation. What is this differential equation? Is actually is similar to the simple harmonic motion equation. No, what is the simple harmonic motion equation? Before going to the simple, I think you all know the simple harmonic equation. The x double dot is equal minus a omega square x. This is the simple harmonic motion equation. Okay, the solution of this differential equation, we can write xt is equal a cos omega t plus b sin omega t. Here the omega is equal k divided by m into square root. Okay, equals omega t plus b sin omega t. You can see this equation is equivalent to the x double dot plus, if you put the k omega square into x, okay, omega square into x. What it means, you can see in a free vibrating system produce the simple harmonic motion equation. What can we say? What is the our conclusion? The free vibrating system without damping produce the simple harmonic motion vibration. Okay, so what is the simple harmonic motion? Let me refresh your memories about the simple harmonic motion. Simple harmonic motion. What is the okay, this equation is a simple harmonic motion equation. Simple harmonic motion equation. What is the simple harmonic motion? Let me explain this simple harmonic motion. I think you all familiar with this one. I just refresh your memories about this simple harmonic motion. Okay. So what is the property of the simple harmonic motion? The property of the simple harmonic motion is always acceleration is proportional to the displacement, and it is directed to the always its acceleration is proportional to the displacement and negative. That means in a simple harmonic motion, let's take its object is producing a simple harmonic motion. Always its acceleration, let's take a certain moment, acceleration is directed to the center of the oscillation, and also it is its magnitude is proportional to the velocity. Its magnitude is proportional to the velocity, and also it is directed always to the center of the vibration. This kind of motions are called simple harmonic motion. One of the very good example for this simple harmonic motion is, you may learn in A level, if object moves on a circular path, if object moves on a circular path, its shadow on a horizontal plane produce the simple harmonic motion. Its shadow, let's take this is moving in this uniform angular velocity omega. If object is moving on a uniform angular velocity in a circular path, its shadow on a horizontal plane, if you take the horizontal plane in this if you consider this is the horizontal plane, so then its shadow follows the simple harmonic motion. This is the very good example for this simple harmonic motion. Based on this simple harmonic this diagram we have obtained in the equations for the simple harmonic motion. Let's take this is t is equal 0, we are starting, this is the point we are starting, and let's take this is the t is equal t position. Then what is this angle in the time t, the omega t, so omega t. Then this displacement from the center is equal x xt, xt is equal, let's take this radius as a cos omega t. Okay, a cos omega t, a cos omega t. Then x dot t, if we take the x dot t is equal minus a omega sin omega t. If we take the x double dot t, that is equal to minus a omega square cos omega t. So then from this equation 1, let's take equation 2, let's take equation 3. From the equation 1 we can write x double dot t is equal minus a, sorry, a in here, x double dot t is equal minus omega square a cos omega t, the instead of the a cos omega t we can put the xt. X double dot t is equal minus omega square into xt. Okay, minus, this is the simple harmonic motion charismatic equation. Then for this simple harmonic motion, what is the periodic time? Periodic time, the t is equal, the one period mean to complete the one cycle of oscillation, the time taken to complete the one cycle of oscillation is called the periodic time. The periodic time is equal to complete the one cycle. That means this object should move on a one complete revolution of this circular path. So what is the time taken for that one? The total distance traveled is 2,5, the angular distance 2,5 divided by the angular velocity omega. Then this is called the periodic time of the oscillation. Okay, periodic time of the oscillation. Then the omega called the circular frequency. Omega is called circular frequency. Omega is called the circular frequency of this oscillation. So then the frequency in hertz. What is for the frequency in hertz? Cycles per second. The frequency in hertz. So what is mean? The cycles per second. Cycles per second. The per second, how many cycles to calculate? How to calculate the per second? How many cycles per second? We have to divide it by periodic time. Then we are getting the per second how many cycles. The t divided by 1 over t mean omega divided by 2,5. Omega divided by 2,5. Then this is, we are getting the answer in hertz. We are getting the answer in hertz. Okay, that means cycles per oscillation, vibration. Okay, then the amplitude of vibration is called the A. The amplitude, that means this distance, is called the A. Okay, this is the simple harmonic motion. So what I explain is simple harmonic motion because free vibrating system produce the simple harmonic motion in its vibrating. Okay, in its vibrating. Okay, let's take the example from this vibration. Okay, first try to work out this example. Okay, the mass of 4 kg lies on a smooth horizontal table and it is attached by a spring to a fixed point as shown in the figure below. The spring has a stiffness of 100 Newton per meter. If the mass is given a small displacement to the right and is then released, neglecting all the frictional effect, what will be the natural frequency? If the mass is struck lightly on at the equilibrium position, so that it is given an initial velocity of 2 meters per second, what will be the equation of motion? So that means okay, let me solve this problem from the free vibration system. Okay, in this example there's a stiffness and the mass 4 kilogram, and the stiffness, the K is equal 100 Newton per meter. Okay, in this example problem is asked to find the system natural frequency. The natural frequency mean the system frequency, system natural frequency mean the oscillation, the frequency of a system, absence of any damping or driving force, called natural frequency. Okay, the frequency of a system in vibration without any driving force or damping force, called natural frequency. That means in a previous example, the system vibrate. It's a natural frequency. This is the frequency of oscillation. Omega is the system natural frequency, because we are mapping this the free vibration system with the simple harmonic motion equation. So then when mapping with the simple harmonic motion equation, for the simple harmonic motion, the system frequency is equal to omega. So in this situation, this omega is represented by the k divided by m square root. So the system natural frequency for the system is omega n is equal to the k divided by m square root. Okay. Then in that way we can find the system natural frequency for the system. Omega n is equal k divided by m into square root. The equation, the k, the 100 divided by the put in Newton meters, Newton per meter, and if k in kilograms, you are getting the answer in radians per second. The square root, that is equal to 5 radians per second. 5 radians per second. That means omega, we are getting the circular frequency. If you substitute this k in Newton per meter and k in the kilogram, you are getting the system circular frequency in radians per second. With the next one, the problem is asking, this is the first one. The second one, if the mass is stuck slightly at the equilibrium position, so that it is given an initial displacement of 2 meters per second, what will be the equation of motion? If stuck lightly mean, if the mass is stuck lightly mean it is at the equilibrium position, there's no any force acting on this mass stuck lightly. So at this position we are given the initial problem is saying the 2 meters per second velocity. That means the t is equal 0. Let's take this is the equilibrium position. T is equal 0 at initial position. The 2 meters per second velocity is given. That means x dot t is equal to 2 meters per second x t. Sorry, I will write this one in this way. Second one, x dot t is equal 0 is equal 2 meters per second, and x t is equal 0 is equal displacement is equal to 0. Okay, displacement equal to 0. So then what is the equation of motion of this system? Xt is equal, we have derived this equation, a cos omega t plus b sin omega t. X then this a and b are constant, have to determine using the boundary conditions. So then this equation we can write in this way also, because already we know the omega, a cos 5t plus b sin 5t. Okay, then AB we are going to determine using the boundary condition. One of the boundary condition we already know, the at t is equal 0, x t is equal 0, what is the displacement? That is equal to displacement is equal to 0. Then t is equal 0 mean here cos 0 is 1, the a plus this term is equal to 0. That means we are reducing this equation to a is equal 0. Then the equation has reduced to xt is equal b sin phi t. Okay, b sine phi t. The equation has reduced to b sine phi t because the a term is equal to 0. So then I am going to take the second derivative of this equation. X dot t is equal 5b cos 5t. Then x double dot t is equal sorry, no need to that one, double dot t. Then x dot t is equal this one, x dot t is equal 0. What is the velocity at t is equal 0? Velocity at t is equal 0 is equal to 2 is equal 5b. This term is equal to 1. So then the b is equal 2 divided by 5. Okay, 2 divided by 5. Then the equation of motion of the system you can write using this way. X t is equal, a is equal 0, b 2 divided by 5. This is the equation of motion for this system. Okay. Then when doing this simple harmonic equation motion problem, you may, mostly important things I have to, these things I think you already know. I just refresh your memories about these things. There, keep remember, if the two springs are connected, K1 and K2, then how to get the resultant stiffness? How to get the resultant stiffness for this spring? What is the resultant stiffness? The resultant stiffness is equal, let's take, I will derive this equation. Let me derive this equation. This is F. Then for this system we can write this, both the spring is subjected to a force. Let's take the deformation x1, deformation x2. F is equal k1 x1, F is equal k2 x2. Okay, k2 x2. Then for this equivalent stiffness should produce the x1 plus x2 displacement in face of F force, so that for this equation we can write F is equal k x1 plus x2. So then we are going to find the x. Then how to find x? From these two equations we can write x1 is equal F divided by k1, x2 is equal F divided by k2, x1 plus x2 is equal x1 plus x2 is equal F divided by k1 plus F divided by k2. Okay, then we can take this relationship in this way. Then yeah, by taking the F into out, F is equal the k1 plus 1 over k2 is equal x1 plus x2. Okay, then further we can write in this way, F is equal 1 over K1 plus 1 over K2 is equal x1 plus x2. Okay, let's take this equation as equation A. Let's take this equation as equation B. Okay, from A and B we can say that the K should equal to this one. So that means the equivalent K value is equal when the spring is coupled 1 over K1 plus 1 over K2. If there's a further springs are attached, 1 over Kn. Keep remember when solving the problem, that is very important. Okay, then what happens if the springs are connected parallelly? How to get the equivalent stiffness? If the springs are connected parallelly, let's take in this situation the K1 and the K2, the displacement is equal to x. So then F is equal K1x. So let's take this is F1 and F2. F1, F2 is equal K2x. So then F is equal the addition of these two, F1 and F1 plus F2. Then this one is equal, F is equal K1 plus K2 into x. If the equivalent system is representing both this spring, the effect of both the spring, that also should produce the x displacement in face of F force. So that we can write this equation, F is equal K into x. By comparing these two equations, these two equations should be equal from A and B. We can write the K equivalent is stiffness, spring stiffness is equal to the K1 plus K2. Okay, this both the equation you may keep remember this both the equation. If there's any further K you have to add like this. Okay, when solving this free vibrating vibration problem, you may remember these things. Okay, then today we discuss about the free vibration without damping. Then we discuss the example problem also. Then next day class we are going to discuss the free vibration with damping, free vibration with viscous damping. Okay, thank you.